Hello. In this podcast, we're going to be looking at Newton's third law of motion. We're going to learn about force interaction pairs, and then we're going to learn how to use Newton's third law of motion to analyze forces in multi-object systems, Atwood machines, pushing or pulling multiple blocks, and multiple pulley systems. First, Newton's third law says for every force there is an equal and opposite force. This creates a pair of forces. Forces always interact in pairs. There are no isolated singular forces. And we call these force pairs interaction pairs. Now, we also can call them action-reaction pairs because the pair includes an action force and a reaction force. So, for example, if the action force is A acting on B, then the reaction force is B acting on A. Want to point out here, both forces happen simultaneously, so it's not like A acted on B and then a split second later B decided to act on A. So choosing which force is the action force and which one is the reaction force is truly arbitrary. They happen simultaneously. Let's take a look at an example here and we'll identify action-reaction pairs. So we have the floor and we have a person standing on the floor and we have the earth below the floor. Let's draw free body diagrams for each object. That's important. We will never find action-reaction pairs on the same force diagram. We've got to draw a free body diagram for each object. For the person, we have the Earth's force of gravity pulling them to the center of the Earth. We have the normal force of the floor pushing up on them. If we look at the floor, we have the normal force of the Earth pushing up on the floor because the floor is resting on the ground. And we have the Earth's force of gravity pulling the floor to the center of the Earth. And we have the person pushing down with a normal force on the floor. If we look at the Earth, we have the normal force of the floor pushing down on the Earth. We have the gravitational force of the floor pulling up on the Earth and the gravitational force of the person pushing up on the Earth. So let's look at these action-reaction pairs. So to be an action-reaction pair has to meet three criteria. First, both forces need to be the same type of force. So they need to be a normal force or they both need to be a gravity force. The second criteria is that they have to involve the same two objects. If the action force includes A and B, then the reaction force has to include A and B also, but in reversed roles. The third and final criteria is they must be pointing in opposite directions. With that in mind, let's look for an action-reaction pair. Well, we have some normal forces. So one of the normal forces we have is the floor acting on the person. So now we need to look for the normal force, the person acting on the floor. And if we come over here to the floor force diagram, we'll see that reaction pair. In our first free body diagram, we also had another force, the force of gravity, the earth pulling down on the person. The reaction force is going to be a force of gravity, the person pulling up on the earth. Well, we need to go over to the earth force diagram and we will find that reaction force right here. Then if we go to the floor force diagram, we have a normal force, the earth pushing up on the floor. The reaction force to this will be a normal force with the floor pushing down on the earth. So we go over to the earth's free body diagram and indeed we find the reaction pair. And then we have another force on the floor's force diagram. That's the force of gravity, the earth pulling down on the floor. The reaction force to this will be the force of gravity, the floor pulling up on the earth. So if we go over to the earth's force diagram, we will find that reaction force. In this simple example, between the floor, person, and earth, we have four action-reaction pairs. Let's move on to some problem solving involving multiple object systems. First, we'll look at blocks A and B being pulled. They're connected by ropes. We have a tension force F1 pulling the system to the right. F3, that could be friction. It could be some other force like a tension force pulling to the left, but it's an opposing force to the motion of the blocks moving to the right. Now when we look at the system, F1 and F3 are external forces, and F2 is an internal force. And we'll see the importance of this when we get to the final solution. What is the acceleration of the system? We need to analyze each block separately. Here are the force diagrams for block A and block B. So if we focus on A, we have F1 pulling to the right, we have F2 pulling to the left. Our acceleration for block A is going to be F1 minus F2 divided by the mass of block A. Looking at block B, we can see that we have the tension force F2 pulling to the right, and we have this force F3, which could be a friction force, doesn't have to be. Our acceleration turns out to be F2 minus F3 divided by the mass of B. Now we know since this system is connected by ropes, and we're assuming that the ropes do not stretch, both blocks need to accelerate at the same rate. That means that the acceleration of A is equal to the acceleration of B and is simply the acceleration of the system. So now we can solve equations 1 and 2 for A, because we can substitute A in for A sub B and in for A sub A. First, we'll rearrange equation 2 for F sub 2, and we wind up with F sub 2 is equal to the acceleration times the mass of B plus F sub 3. We'll substitute this into equation 1 and solve for A. And when we do that, after some algebraic manipulations, we wind up with the acceleration of the system is equal to F1 minus F3 divided by the system mass, MA plus MB. Notice the internal force F2 does not show up or impact the acceleration for the system. And that is true of all systems. When we are calculating the acceleration of the system, the internal forces, because of Newton's third law, wind up canceling each other out. Notice that the system mass here of MA plus MB, we are making the assumptions that the mass of the ropes are insignificant compared to the mass of the blocks. Let's move on to another system. Let's look at the Atwood machine. So we have the original Atwood machine with a pulley, a rope attaching two masses at opposite ends. We're going to assume the rope and pulley are massless and the rope does not stretch. First, we do our individual force diagrams. Block 1, we have the weight of the block acting downward. We have the tension force of the rope acting upward. And in block 2, we have the weight of block 2 pulling down, and we have the rope tension force pulling up. Because of Newton's third law, the tension throughout the entire rope, and this is true of all ropes, the tension will be the same. A pulley is a simple machine, and one of the things it does is it changes the direction, and that causes us to make an adjustment in how we analyze our problems. So when a pulley is involved, you need to define the positive direction based on the movement of the rope. So let's let block 2 moving down be positive, which means block 1 moving down would be negative. Let's solve this problem. I just put our sketch and our free body diagrams up here for reference. Solving for the acceleration of block 1, it's the tension force minus the weight of block 1. Remember, block 1 moving down is the negative direction. And the acceleration for block 2 is the weight of the object minus the tension force, because block 2 moving down is positive direction. And of course, both of these are divided by the respective masses, m sub 1 for A1 and m sub 2 for A2. Since the rope doesn't stretch, the acceleration of 1 and 2 are the same, and they equal the acceleration of the system. So now we need to solve one of the equations for F sub t and substitute that into the other equation. I've chosen to take equation for block 1, rearrange it to solve for F sub t, and then I plug that into the acceleration equation for A sub 2. This is what we get. We can do some simplifications, and we wind up with the acceleration is equal to g, the acceleration due to gravity, times the difference in the masses, m2 minus m1, divided by the system mass, m1 plus m2. Special note here, if m2 is greater than m1, then the acceleration would be positive, and if m1 is greater than m2, then the acceleration would be negative. And keep in mind, we said that the rope moving to the right, block 2 going down, is the positive direction. Let's move on. A modified Atwood machine. So here we have block 1 and block 2 attached by a rope that doesn't stretch and a pulley system. Let's do our forces. We have the weight or force of gravity of m2. We have the tension force of the rope pulling up. We'll call that T. Because of Newton's third law, the tension at the other end of the rope, which is pulling block 1 to the right, is also magnitude T. We have the force of gravity pulling down on m1, and that's equal to m sub 1 times g. We have the surface, the table surface, pushing up with a normal force n, that balances out the weight pushing down. And we have a friction force to the left, which will have a magnitude of F. So now we can go ahead and set up our acceleration equations for each block. For block 1, it's the tension force minus the friction force divided by the mass of block 1. And for block 2, it's the weight of block 2 minus the tension force pulling up on block 2 divided by the mass of block 2. We have our standard assumption that this rope does not stretch or compress, therefore the accelerations of both blocks are the same and they are the system acceleration A. We're going to take one of the equations and solve it for t. I happen to pick the equation for the acceleration of block 1, rearranged it for t, and now we're going to substitute this expression for t into the other equation. And we're going to wind up with A is equal to m sub 2g minus m sub 1a plus f divided by m sub 2. Now we have to solve for acceleration, so after some algebraic manipulations, we wind up with the acceleration of the system is equal to the mass of block 2 times the acceleration due to gravity minus the friction force divided by the system mass, which is mass 1 plus mass 2. We're making the assumption that the rope's mass is insignificant compared to blocks 1 and blocks 2. Notice that if we have no friction, this term goes away. So we can use this general equation for the modified Atwood machine with or without friction. Now, let's look at pushing multiple blocks. So here we have a force that's pushing block 1, and block 1 in turn is pushing block 2. We may just intuitively come to the assumption that this force pushing block 1 is equal to the force of block 1 pushing on block 2. However, we're going to go through this analysis and find out that that is incorrect. So do not make the assumption that the force acting on block 2 is the same as the force acting on block 1. Let's look at the free body diagrams for both blocks. For block 1, we have force F acting to the right, and we have the block 2's normal force being exerted on block 1 acting to the left. And then for block 2, we have the normal force of block 1 pushing on block 2 to the right. Next, we set up our acceleration equation. So the acceleration of block 1 is equal to F minus the normal force of block 2 pushing back on block 1 divided by the mass of block 1. For A2, we have the normal force of block 1 pushing to the right on block 2 divided by the mass of block 2. These normal forces of block 2 and block 1 pushing on each other through Newton's third law are equal to each other. And since the blocks are touching each other, we know that A1 and A2 are equal because the blocks are accelerating at the same rate, at the rate of the system. So we can go ahead and do our calculations here. Looking at our equation for the acceleration of block 2, we can see that the normal force of 1 acting on 2 is equal to the acceleration of block 2 times the mass of block 2. We can go ahead and make this substitution into the block 1 acceleration equation in place of that normal force. We can do some rearranging, and we wind up with the acceleration of the system is equal to the force F divided by the system mass m1 plus m2. Notice that in determining the acceleration, these normal forces between block 1 and block 2 do not figure in the final equation, and that's because they are internal forces. And so we're seeing that recurring theme that internal forces within a system do not play a role in the system equations. Also, if we were interested in finding out the strength of the normal force of block 1 pushing on block 2, it is equal to the force F times the mass of block 2 divided by the system mass. Suppose in this example, instead of the force pushing to the right on block 1, we had set it up where the force was pushing to the left on block 2. In that case, then, the normal force of 1 pushing on 2 would be equal to the force F times the mass of block 1 divided by the system mass. Now, we haven't looked at this case with friction, but if we were to take a look with friction, the acceleration would be the force pushing to the right F minus the individual friction forces of blocks 1 and 2. Note in a problem you may just be given one friction force for both blocks combined. And so it's that net force divided by the system mass. And to find the normal force of 1 pushing on block 2, it's the force F times the mass of block 2 minus the friction of block 2 divided by the system mass. And if we had the force pushing to the left on box 2, we would adjust the force equation the same way we did over here. Let's move on now and look at multiple pulley systems. We have a system of 2 pulleys, one attached to a fixed surface, presumably a ceiling, and we have another one that's attached to the object with mass of m that we want to raise. We want to take a look at the force diagram. Clearly, we're going to be pulling down, or something's going to be pulling down on the rope to lift this block. Our first force we're going to look at is the force of gravity, Earth pulling down on the block, and of course the magnitude of that is going to be the block's weight. We then have this rope pulling up on the block and down on the pulley. I'm going to treat this pulley and this block as just one system. Within the system, I'm going to ignore these forces here because they clearly are going to balance each other out. Moving on then, we have the tension of the rope pulling up on the left-hand side of the pulley. We'll call that T1. Also, we have the rope on the right-hand side of the pulley pulling up, and we'll call that tension T2. From the free body diagram, we can set up this Newton's second law equation, and so the sum of these tension forces T1 plus T2 are going to be equal to the weight of the block plus the mass of the block times the acceleration of the block. We know from Newton's third law that anywhere on the rope the tension is the same, so T1 is equal to T2. Therefore, we can come up with an equation for the tension in the rope, and it's 1/2 the mass of the block times the sum of the acceleration due to gravity and the acceleration of the block. And of course, from Newton's third law, we know that the force on this end of the rope has to be equal to the tension anywhere else in the rope. So this will tell us how hard we have to pull on the rope in order to achieve this acceleration. Pulleys are a type of simple machine, and they have two functions. One, they can change the direction of the force. So in other words, we can, in this example here, we are pulling down and it's causing an object to move up. The other thing it can do, as we saw in this system, is it can reduce the amount of force needed to lift an object. We can achieve even greater reductions in force if we use even more pulleys. In these two systems, we're using a total of 3 pulleys. I want to point out this MA does not stand for mass times acceleration. It stands for mechanical advantage. So this is telling us approximately the reduction in force needed to lift these objects, these blocks at the bottom. Both systems use 3 pulleys. In this system, the third pulley is attached to the ceiling, and in this system, the third pulley is attached to the moving block. In this system here, on the left, we see that the rope is pulling up on the pulley that's attached to the block in 3 places. This means it's creating 3 tension vectors. These 3 tension forces are balancing out the weight of the block and the weight of the moving pulley. Therefore, these tension forces are approximately 1/3 the weight of the pulley and the block. And the reason they're not exactly 1/3 the weight is, notice, of the 3 vectors, only this one is going perfectly vertically. These are going a little bit horizontal as well as vertical. That means that it's going to increase the amount of tension needed to balance out the weight of the pulley and the block. So the actual tension force in the rope is going to be a little more than 1/3 the weight of the pulley and the block. But you can see we gained an advantage of 3 times. The force is about 1/3 of the weight we're moving. Moving over here, by adding the third pulley to the moving block system, we create 4 points of tension force where the rope is pulling up on the pulley system attached to the block. So the weight of these 2 pulleys and the block is spread out over 4 tension vectors, and they will be approximately 1/4 of the weight of these 2 pulleys and the block. In actuality, they'll be a little more than 1/4 the weight, and that's because 3 of the vectors are not going perfectly vertical. And whenever you have that, you wind up needing more force to offset the force of gravity or weight. This system, notice just by changing the pulley down to the moving block instead of making it part of the fixed ceiling system, it increases our mechanical advantage from 3 to 4. To make the final connection, the mechanical advantage of this system over here is 2, because the rope contacts the pulley and block system in 2 places and has 2 tension vectors to offset the weight of the block and the pulley. Let's look at one more system of pulley. In this system, there are 2 ropes, one in green and the other one in blue. The previous systems we were looking at had multiple pulleys, but just 1 rope. Here we have multiple ropes and multiple pulleys. We can see that both ropes are connected to the ceiling at some point. In this problem, we are given a block of mass M on the left-hand side of the blue rope, and we're asked to find out what the mass of this block here attached to pulley C has to be in order for the system to be in equilibrium. Now, by equilibrium, we mean it could either be stationary or moving with constant velocity. We'll solve this the same way we did in the previous slide. We have to start with free body diagrams, starting with what we know, which is over here on the left-hand side of the system, and working our way through the blue rope going over pulley A and pulley B. Then with pulley B, we need to start with the green rope and work our way through. And you can see the force diagram set up here. In the end, it turns out that this block can have 4 times the mass as our block on the left. Or in this case, since it was a 10 kilogram block here, this block can be 40 kilograms to keep the system in equilibrium. If this mass were less, then we're going to have this block fall down and this block go up. If this mass is greater, then we're going to have this block accelerate down and the original block accelerate up. This ends our lesson on Newton's third law. I hope this helped, and have a good day.